Swayam Prabha. Digital India. Educated India.
Welcome back. So next we are going to look into this thing called condensed fuel vaporization. Now, as I have told you that in a gas turbine engine or aero gas turbine engines, combustion is so very important. It is indispensable because of the fact that you can burn liquid fuels, and the heat that is generated of that you can use it for propulsion or for power generation, right. So as a result of that, understanding how the fuel vaporizes, because in air breathing engines combustion happens only in gas phase. Okay. So for that, understanding how the fuel vaporizes is very important, because only after vaporization happens you can have mixing. That is, you can have the fuel and the air mix at some point, and then you can have a flame. So a vaporization of the condensed fuel is a very key process in understanding combustion of liquid fuels or combustion in air breathing aero engines. Okay. So we will start with the one dimensional problem in Cartesian coordinates, and we will consider a thermally insulated beaker. Okay. Let us say this is the thermally insulated beaker, okay, and this is one dimensional. We are solving the problem only in this direction, which is the x direction. From x is from here. Okay, we will solve only in the gas phase actually. So this beaker contains this liquid, which can be say water, and this is the interface. Okay, between air and water, and on top here there is a breeze which helps keep the mass fraction of the water vapor, because water vapor is continuously formed from here, okay, which keeps the mass fraction of the water vapor here fixed. So that mass fraction that is kept fixed is Y1L, and its temperature is also kept fixed by this convective flow, but that is, this convective flow is not a part of our problem. Our problem is only focused into this region. Okay. So between x equal to 0 and x equal to L, and here at the just above the interface the fuel vapor mass fraction is Y10, and the temperature at that point is T0. Okay. So now as the fuel, as this liquid which is water or a fuel which vaporizes from here, okay, that, and you know that the liquid meniscus will come down, and of course the liquid is vaporizing here and it is going out here. So there is a continuous flow, there is a bulk flow of fluid that is happening, and as a result, because there is no convection inside, there is no pressure gradient inside this thing, the only thing that drives is essentially this diffusion flux. Okay. So this diffusion of this of the liquid is essentially driving the convection, and that is called the Stefan flow. That is, the net loss of water signifies the presence of Stefan convection. So this is the thermally insulated beaker of water, is this undergoing vaporization. This is undergoing the vaporization from here, and of course for vaporization you need the latent heat of vaporization, and that is supplied by the ambient. So essentially heat is diffusing from this direction from the top to bottom, and the fluid is and the water vapor is diffusing from the bottom to top. Okay. So as a result of this, we will see that the heat and mass transfer of this problem will be intricately coupled. Alright. So this is the problem at hand that we have. So then the goal is to determine the vaporization and the condensation, vaporization and condensation rate and the temperature of water in the beaker. Alright. So of course this is a steady problem, there is no net change of the species profiles inside this, inside this this beaker that is happening, and it is a one dimensional and it is a steady problem. And also you see that by that, if we apply the continuity equation, we get this d rho u dx is equal to 0, and then it means that rho u is equal to this the flux, the mass flux is essentially is equal to constant. Now we can also apply species conservation for I is equal to can be the I equal to 1 can be the water vapor phase, and I is equal to 2 can be the air phase. Of course, you have to see that there is also air here, okay, because if there is a species profile which is, say, if this is the species profile direction of y1 which is going down like this, of course there has to be air which has to be like this, because the mass fraction, this is y2, has to be go down like this, because the sum of y1 plus y2 must always be equal to 1. Okay, so for that if you consider the species conservation, this is f times dy I dx minus d dx of rho d dy I dx, okay, equal to 0. Of course, f is equal to rho u, because the actual formula is like this, that rho u dy I dx minus d dx of rho d times dy I dx equal to 0. So that is the thing. So instead of rho u we have put f, because that is a constant, and then if we integrate it once, okay, we get this thing, that is f y I minus rho dy I dx is equal to constant, and that is equal to f I. Why f I? Now that is an interesting thing. For that you have to understand that what are those, that is why I have written this, that what are these two things, okay. So we can say that this guy, we have to not this guy, we have to look into this guy, that is what is f y I minus rho d dy I dx, okay. What is this thing? And we can write this f as rho u times y I minus rho d dy I dx, okay. Now this guy, okay, rho u y I this is, you see, rho times y I can write this as rho I, okay, times u, all right, minus we can write this as yi by yi times rho d dy dx, okay. So rho I times u minus, we can just combine these two things, and we can write it as rho I times d ln yi dx, okay. Now what is this guy? This is nothing but the species diffusion velocity. So rho I times u minus rho I times v. What is this? That is nothing but rho I times ui, okay. So this ui, this rho I times ui is nothing but fi, okay. That is a flux of the species I, okay. This is the bulk velocity, this is the species species diffusion velocity, okay, and this is the species velocity ui or vi, right. This was vi. So this rho I times vi is nothing but the species flux of fi. So that is why this, you get this when you take the sum of these two things, the constant that you get is nothing but the species flux, which is fi. So fi is essentially the sum of the diffusive and the Stephan convective fluxes. So this is the Stephan convective flux and this is the diffusive flux. So this is the sum of these two. So but as we know that if we talk about fi, for if f1 is not equal to 0, because that is the species, this is the water vapor that is diffusing, okay, that is the motion of, that is the flux of the water vapor. But f2, that is air, that is not moving and that is stagnant, and that is not moving because that is not condensable at the interface, and that is stagnant, and as a result of that, that f2 is equal to 0. So, the species 1 is essentially water, is given by F1 is equal to F minus F2, because F1 plus F is nothing but F1 plus F2, and this F is F2. If F is equal to 0, then it becomes F1. So, F is essentially is equal to F1. So, we can replace this Fi, if it is 1, we can replace this F1 with F. Okay. So, then we get Fy1 rho dy1 dx is equal to F is equal to F1, and because this is F, we get essentially F of yi minus 1. We can write this equation as this, rho d dy 1 dx, okay, and we can write this as F dx is equal to rho d dy1 by y1 minus 1. Okay, and then we can integrate this, and we will end up with this. We integrate between 0 to L essentially, and this is between integrate this between y1 0 to y1 L. Okay, and we will get with this, we will get this F to be rho d by L times log of 1 plus b mv, where mv is a mass transfer number, which is nothing but this quantity. Okay. So, this essentially is essentially the what you see, this mass transfer number is nothing but the difference between the species mass fraction at the boundaries, that is, this is nothing but this is the y10, and this is where you have y1L. So, this is the difference between this divided by 1 minus y10. Okay. So, that is the thing. So, it has, you see that this flux, this net mass flux has a logarithmic dependent on this mass fluxion mass transfer number, which BMV is given by 1 minus y10 minus y1L divided by 1 minus y10. And of course, you have vaporization when this is positive, and we have condensation when this is negative. And of course, you see that when you have negative, this y1L should be greater than y10. So, if the ambient mass fraction of the species 1 is greater than the mass fraction at just above the interface of vapor, just above the interface, then you have condensation. Okay. And of course, if it is slow vaporization, that if a BMV is small, much less than 1, then you can approximate the logarithm to be linear, and you get rho d log by L times log BMV. But of course, you see that when this becomes large, you have a logarithmic dependence which tells you that the F essentially slows down with increase in BMV, and it is just not directly proportional to BMV. The proportionality only holds when this is very small. Okay. Now, you might think that the problem is complete, it is solved, but it is not, because you see that in this flux, okay, in this vaporization, in this mass flux F, we do not know BMV, because we do not know what is our y1, we do not know what is our y10 essentially. Okay. So, this is y10, that is problem is incomplete, because only species conservation or vapor concentration at the surface, that is y10, is not known. Okay. So, we need to know y10, essentially we need the energy conservation, and that is the energy conservation is nothing but rho u Cp dt dx minus dt ddx of lambda dt dx. Of course, we do not have right hand side in either of these cases, because there is no reaction. Okay, by neither in the species conservation equation you have any right hand side, neither in this one you have any right hand side, because there is no reaction. And what if you integrate this, what you get is essentially f Cpt minus lambda dt dx is essentially equal to constant. And then you have to, what you have to do is you have to apply energy conservation at the interface. When you say that the energy that goes for evaporation, that is supplied purely by conduction. So, as a result of that, this lambda dt dx equal to 0 is essentially the mass flux that is evaporating times the latent heat of vaporization, that is QV. And using that, you can apply the energy conservation, and we get f Cpt minus T0 minus lambda dt dx is equal to FQV. And then if we integrate, we get we find that f is equal to lambda by Cp times by L, and that is the distance between the free stream between the outside and the surface, and that is times once again ln 1 plus BHV, but this BHV is nothing but the heat transfer number, and it is Cptl minus T0 by QV. This once again shows that we get exactly the similar things, because in the previously we got f is equal to rho d by L, as you see here, rho d by L times ln of 1 plus BMV, okay, by L times ln 1 plus BMV. Okay. So, this and these have exactly very similar form because the nature of the equations is essentially similar. Of course, you see that this rho lambda by Cp is, and this is for characteristic diffusivity for the heat transfer, this is the characteristic diffusivity for mass transfer. Of course, we can assume Lewis number to be 1 and these two can be same, but this is not required now, and but this is the heat transfer number that we have obtained that goes into here. Okay. So, this heat transfer number is nothing but BHV is equal to Cp times TL minus T0 by QV. Both this heat transfer number as in mass transfer number, we can think of this as the driving potential that drives the species flux or the heat transfer actually. So, larger this BMV, the more is the species flux, more is the mass flux F of more is the evaporation. This F is the essentially the mass flux of water, because there is no mass flux of air that is convecting. So, this F is essentially contains only the mass flux of water. So, it is essentially the evaporation flux. So, this evaporation flux is larger for larger B, either M by either MV, that is the mass transfer number, or the heat transfer number. So, this acts as essentially a potential, and this potential you see depends on the difference of the temperatures between the free stream and the surface, or between the in terms of the temperature difference or in terms of the mass fraction difference. Okay. So, larger the mass fraction, larger is the evaporation rate, larger is the temperature difference, larger is evaporation rate. And of course, you have BHV when this is larger, you have condensation. When this is positive, that is when the temperature difference between the outside and the D0 is positive, you have evaporation, and then when it is negative, you have condensation. Okay. Then we can if we say that the Lewis number, if the Lewis number is equal to 1, then of course you see that these two becomes then these and this becomes same, and of course these two F are same, and this both are represents the mass flux or the mass flux of water vapor that is escaping the interface, and then this log becomes can be equated, and for this to be equated, of course this inside this mass transfer number and the heat transfer number has to be same, and we get this that is relation for the heat transfer number equation and this to be same, and using this relation essentially you can solve for y10, which was actually holding us to describe the F, because F contained the mass transfer number, and the mass transfer number contained y10. So, y10 as you see is essentially is a function of T0, and that is equal to y1L plus BHV divided by 1 plus VHV. And this is still not solved. It is still not solved because this T0, that is the temperature at the surface, is not known, and for that we need phase change kinetics. Okay. And for that we have to assume the equilibrium state, and where we assume that this species, the same species, goes from a liquid phase to a gas phase, and of course the phase change rate is, I assume that the much faster than the gas phase diffusion rate. Okay, and then we can apply this thermodynamic relation, which is called the Clausius-Clapeyron relation, which says that the partial pressure at the reference temperature T is essentially equal to the reference pressure, which can be assumed to be 1 e to the power of QV, that is the latent heat of vaporization, divided by R0 times 1 minus TBN minus 1 by T, and this is once again this can be a reference temperature, whereas this gives the relation between Pi and T, that is a partial pressure and temperature when there is a phase change, and we can assume that if this is 1 bar, this becomes the essentially the normal boiling point. Okay. And then you can convert this partial pressure into essentially mole fraction, and from mole fraction you can get to mass fraction. So, then using these two relations simultaneously, this one and this one can iteratively solve for and find F and T0 together, and the liquid temperature so found is the wet bulb temperature. So, this solves our this essentially solves our this essentially solves our problem of estimating the evaporation rate or the evaporation flux from a liquid pool, in which where the top of which is there is continuously removal of the vapor flux that is that is coming out of the liquid pool. So this is very important, and we can now in a position to tackle the more practical problem of droplet evaporation from droplet evaporation, where the droplet contains essentially can be containing a water or can contain a liquid fuel, and then for the liquid fuel case we can use this further to essentially again find out what is the how does the droplet burn, and then what we'll do is that we'll use these ideas that we have just developed here, use these ideas to essentially describe the droplet evaporation rate, and then once we have the droplet evaporation rate, we can use the previous this non-premixed flame coupling function ideas, and we will essentially couple these two things, that is this evaporation analysis and the non-premixed flame coupling function analysis, and using these two we can describe the droplet combustion. So that we will do in we will be doing in the next class. So droplet vaporization, and this is the d square law of droplet vaporization that we will do in the next class. So thank you very much.